All right, there are two things that are unique about problem 30 compared to the other inclined plane problems that you've seen. And that is that in an inclined plane problem, oftentimes you don't need an applied force. If I'm skiing and I'm on a hill, I'm probably going to go down the hill because there's going to be a component of my weight that will be enough to overcome whatever friction exists so that I can move down the hill. But in this example, we're going to have a applied force because we're now going to try and go up the hill. Now we would naturally go down the hill, so I'm going to make this now, the slope is 25 degrees. So 25 degrees is not a real steep hill, so don't make it look like that. Make 25 degrees look something like what 25 degrees would be. So that is going to be my angle, and so I'm going to write that's going to equal 25 degrees. And the skier is being pulled up the slope. So I'm going to have a skier on this hill. So there's the skis, and here's the skier. And let's say they're going to be holding on to the tow rope to go up the hill. Now, the first force I always draw is still going to be my weight. So when you're doing an inclined plane problem, you want to first draw your weight because that's the one that's going to be broken into its components. So I'm going to have the weight straight down. And I'll label it over here on the side. That's the weight. Now, normally we have down the hill is the positive direction, and up the hill would be the negative direction. But for this problem, I'm going to turn things around because I usually like my positive direction to be the direction the object actually moves in. That way, if it's accelerating up the hill, I don't have to try and remember to put a negative for my acceleration. So I'm going to have my x is going to go up the hill, and my y is perpendicular to that. So once the weight is on the picture, now I'm going to take the weight and I'm going to break it into its two components. So I'm going to go in this direction, and I'm going to make sure I'm perpendicular to the hill, and I'm only going down far enough so that when I complete the triangle, my other line will be parallel with the hill, and those two arrows will be perpendicular to each other. So my wx is going to be like that. And notice their arrows also. I saw in the last quiz, people were just writing lines. They were making triangles, but they weren't writing the direction. And if you do that, you'll lose points on the test because each one of these has to represent a vector, an arrow. So this is going to be your wx, and this is your wy. And whatever the angle is of the hill, that's going to be the angle right there. I also know that I have a right angle between my x and my y. That doesn't look good. Let's see if I can make it better with this. All right, so that's my right triangle. Now, like I said, there's an applied force pulling me up the hill. So I'm going to have an arrow in this direction, and I'm going to make it about this length. And I'll explain that in a second. So the applied force is going to be that. And actually in this problem, if you read it, that's the unknown. It says find the magnitude of the force that the tow bar exerts on the skier. So that is going to be my unknown. And let's see, what else do we know? We know the mass of the skier. So somewhere over here, I'm going to write the mass. The mass of the skier is 55 kilograms. And the coefficient of friction is given in the problem as 0.120. So those are some of the facts that were given. Now, because it's a coefficient of friction, there's going to be friction. And friction always opposes motion. So since this person is going to be going up the hill, then friction is going to be down the hill. So friction is going to be down the hill. And I'm going to label that. And if I look at these two arrows here, this one and this one, if I add them together, like if I put this one on the end of that, the length of that should be the length of that for this problem, because it does say that the person is being pulled at constant velocity. So constant velocity means that the acceleration is 0 meters per second squared. So that's all the information from the wording, and we've got the diagram ready to go. So once that's done, we're now going to get our descriptive equation. So we sum up our forces in the x direction. What will my equation be? Now look, my positive direction is now up the hill. So keep that in mind when you tell me what the descriptive equation is. What will my descriptive equation be in this problem? Yes. Right, FA minus WX minus friction equals MA. That's my equation because I'm calling up the hill positive. And then when I sum up my forces in the y direction, well, I don't have my picture complete yet, right? It's not complete because which one did I forget to put in? The normal force. So there's going to be the normal force is going to be in that direction. So that's going to be my normal force. So I have two blue arrows. And what's my descriptive equation going to be for that? Fn minus Wy equals 0. And in this particular problem, we also know that this one's going to be 0. Because if my acceleration up the hill is 0, then ma is 0. So both of these actually equal 0 in this problem. It's moving up at a constant velocity. So now we need to just start solving things. So what's the first thing we can solve for? The weight. So the weight is mg. So we're going to have mg. The mass is 55 kilograms. G is 9.8 meters per second squared. And what does that work out to be? 55 times 9.8. 539 newtons. So there's our weight. Now what can we solve for? What can I get now? Wx and Wy. If I know the weight and the angle, I can get my two components. So my Wx is going to be W times either the sine or the cosine. So if we look at the picture, that's the opposite side. Wy is the adjacent side. That's the opposite side from that angle. So when we're looking for the opposite, when we're also involving the hypotenuse in the solution, then we're going to use sine. So Wx is going to be W times the sine of the angle. So that's going to be 539 newtons times the sine of 25 degrees. And that will equal what? Something in the 200s, right? 227.8, so we'll say 228. Because we're rounding now to three significant digits, 228. Now I can get Wy, right? So we have Wx, we'll get Wy. So Wy is going to be W times, it has to be the cosine of theta, because that's the, Wy is the adjacent side of this triangle. So it's the cosine. So we're going to have 539 newtons times the cosine of 25 degrees. Now that number should be bigger than the other one, because if I look at the picture, my blue arrow is bigger than my red arrow because I did draw it pretty much to scale. That's about a 25-degree angle. So this should be a much bigger number. And what do we have for that? 488, which is much bigger than, it's more than twice the size of the other one. So we have Wx and Wy. Now what do I know? It's the next thing I know now that I know the components. I know the normal force because these two are going to be equal. So I can say that Fn equals Wy equals 488. So that takes care of Fn. Now what can I solve for? Friction. I can solve for friction because I know the mu. I know the coefficient of friction. So friction is mu Fn. So that's going to be 0.120 times 488. And that will be somewhere around 50. What's that going to be? What is it? 58 point. Okay, so I'm actually going to write this number only to two significant digits. 59 then? And I'm going to write 59 because I've already established that I'm rounding up my forces to the nearest whole number. So I don't want this one number to be the nearest tenth when the others are to the nearest whole number. So now that we know that, there's only one thing left to solve for, and that's what? Fa, because I know this and this, that's 0. So I can now use this to solve for the applied force. So the applied force is going to be, when I move these two to the other side, they're both going to be positive on the other side. So it's going to be Wx plus friction. So Wx is 228 newtons, and friction is 59 newtons. And if you solve that, that looks like 287 newtons. And that's the solution to that. So bring it down here. So I got